We exist in a world defined by dimensions. Think about any object you can see or touch. It has length. This tells us how long the object stretches from one end to the other. It also possesses width. This describes how broad the object is side to side. And crucially, it has height. This measures how tall it stands from its base to its top. These three: length, width, and height are the fundamental spatial dimensions. We navigate our lives using them every single moment, often without a second thought. Understanding these is our starting point on this cosmic journey. Let's consider a simple, everyday example. A shoebox. Its length is one clear measurement. Its width is another distinct measurement. Its height extends upwards, completing its form. These three numbers perfectly define the space that the shoebox occupies. You can pinpoint any spot on or inside that box using just these three coordinates. Now, think bigger, your own room. You can measure its length, its width, and its ceiling height. These dimensions give your room its volume, the space you move within. Every physical thing, from a tiny grain of sand to a giant star, exists within these three spatial dimensions. Then came Albert Einstein, a true visionary. He proposed a mind-altering idea. He suggested there is another dimension we must consider. This dimension is time. Now, time isn't something tangible like the sides of a box. You cannot reach out and grasp it, yet it's absolutely essential for describing where and when events occur in our universe. An event doesn't just happen at a particular location in space. It also unfolds at a specific moment in time. Both where and when are critical pieces of information. Thus, time joins length, width, and height as the fourth dimension. When we weave these four dimensions together, three of space and one of time, we get a new, grander concept. Scientists call this unified framework spacetime. Imagine it as a vast four-dimensional stage. Every event that has ever happened, is happening, or ever will happen in the cosmos plays out upon this stage. It's like a universal coordinate system. Three coordinates tell you an object's position in space. The fourth coordinate tells you its position in time. Everything possesses its own unique address in space-time. This idea is the bedrock of Einstein's revolutionary theories about the universe. Einstein didn't just combine space and time, he gave this space-time a physical quality. He asked us to imagine space-time as a kind of flexible fabric. Picture a gigantic cosmic trampoline, stretched out perfectly taut and flat. This represents the underlying structure of the universe when it's empty. In regions far removed from any significant matter or energy, this space-time fabric remains smooth and undisturbed. Objects moving through such empty, flat space-time would naturally travel in perfectly straight lines, their paths unaltered. This is the universe in its most serene state, a blank canvas. This space-time fabric, however, is not merely a passive backdrop. It is a dynamic entity, profoundly influenced by the presence of matter and energy within it. Think about our cosmic trampoline again. If nothing heavy is placed upon it, the surface stays perfectly level. This is analogous to space-time far from any stars, planets, or galaxies. An object, like a small marble, could glide across this flat surface in a straight line, its motion simple and utterly predictable. This undisturbed, flat space-time represents the universe in its most basic geometrical state, a tranquil expanse that can be shaped and molded. Now let's introduce mass into this picture. Mass is essentially a measure of how much stuff an object contains. Our sun, for example, has an enormous amount of mass. The Earth has considerably less mass than the sun, but still a very significant amount. Even you, reading this, possess mass. When you place an object with mass onto our metaphorical space-time trampoline, something dramatic happens. The fabric sags, it curves, it deforms under the weight of the object. The more massive the object, the deeper and more extensive the indentation it creates in the fabric. Consider placing a heavy bowling ball onto the stretched trampoline. It creates a noticeable deep curve. A much lighter tennis ball placed on the same trampoline would create a far smaller, shallower curve. This is precisely how mass interacts with space-time. It warps it. It distorts its very geometry. The sun, being extraordinarily massive, carves out a huge curve in the space-time surrounding it. Planets like Earth, with their lesser masses, create smaller, more localized curves. This isn't just a simple dip, it's a fundamental bending of the interwoven structure of space and time itself. For many centuries, humanity thought of gravity as an invisible force. Sir Isaac Newton brilliantly described it as a mysterious pull that exists between any two objects with mass. But Albert Einstein offered a completely new and revolutionary perspective. He proposed that gravity is not a force pulling objects towards each other at all. Instead, Einstein declared that gravity is the manifestation of warped or curved spacetime. Objects are not being actively pulled by some unseen tether, they are simply following the contours and curves present in the spacetime fabric. This was a monumental shift in our understanding. Let's return to our trampoline analogy. Imagine rolling a small marble across the perfectly flat surface of the trampoline when nothing else is on it. The marble will travel in a straight line, unimpeded. Now place that heavy bowling ball in the center of the trampoline. The fabric around the bowling ball curves significantly. If you now roll the marble again, not aiming it directly at the bowling ball but nearby, its path will inevitably bend. It will curve inwards towards the bowling ball. This happens not because the bowling ball is pulling the marble with a force, but because the fabric itself is curved, and this curvature guides the marble's motion. This is precisely what occurs with celestial bodies like planets and stars. The sun, with its immense mass, warps the space-time around it in a profound way. The Earth, as it moves through this warped space-time, naturally follows the curve created by the sun. This continuous following of the curve is what we observe and describe as Earth's orbit. From Earth's perspective, it feels like it's traveling in a straight line through space-time. But because space-time itself is bent and distorted by the sun's massive presence, Earth's path becomes an ellipse, a closed loop around the sun. This is gravity in action, a cosmic dance dictated by the geometry of the universe. This curvature of space-time doesn't just affect the paths of objects, it also influences the flow of time itself. This extraordinary effect is known as gravitational time dilation. Simply put, time runs slower in stronger gravitational fields, where space-time is more curved. This means that time passes ever so slightly slower for someone standing on the surface of the Earth, compared to someone in orbit high above, further away from Earth's mass. This isn't just a theoretical curiosity. Global Positioning System, GPS satellites must meticulously account for this effect. Their internal clocks would quickly become inaccurate if they didn't adjust for both their high speeds and this gravitational slowing of time. The degree of spacetime curvature is directly proportional to the amount of mass present. It also depends crucially on how concentrated that mass is within a given region of space. A planet like our Earth creates a relatively gentle curve in spacetime. We experience this gentle curvature as our everyday force of gravity, keeping our feet firmly on the ground. The Sun, being vastly more massive than Earth, carves out a much deeper and more extensive curve. This larger curvature dictates the orbits of all the planets in our solar system. Different celestial objects produce different levels of distortion in the cosmic fabric, each revealing the strength of their gravitational influence. Now, let's dare to imagine an object with an absolutely enormous amount of mass. Or, picture an object whose mass has been squeezed into an incredibly tiny, almost infinitesimal volume of space. Such conditions lead to what can only be described as extreme space-time curvature. This is the extraordinary realm where we encounter black holes. A black hole is typically formed when a very massive star, many times the mass of our Sun, exhausts its nuclear fuel and collapses catastrophically under its own immense gravity. Its entire mass becomes concentrated into an infinitesimally small point known as a singularity, a place where our current laws of physics simply cease to apply. At the singularity at the heart of a black hole, space-time is theorized to be infinitely curved. The gravitational influence is so overwhelmingly powerful that absolutely nothing can escape its grasp. Not even light, which is the fastest thing in the entire universe, can break free once it crosses a certain boundary. Let's revisit our trampoline analogy one last time. Imagine the bowling ball is now so incredibly heavy that it rips right through the fabric of the trampoline, creating an infinitely deep, inescapable well. Anything that rolls too close to this rupture inevitably falls in and cannot ever get out. This point of no return surrounding a black hole is called the event horizon. Once any object, whether it's a speck of dust, a planet, or a beam of light, crosses the event horizon of a black hole, its fate is irrevocably sealed. It will be inexorably drawn towards the central singularity. Black holes represent nature's ultimate cosmic traps, the most extreme manifestations of Einstein's theory of general relativity in action. They vividly demonstrate how mass can bend and warp spacetime to such an astonishing degree that it fundamentally alters the behavior of everything in its vicinity, even light itself. They continue to be some of the most fascinating, mind-bending, and mysterious objects in the entire cosmos, challenging our understanding of reality.